Hey everyone, hello. So, as you may recall from class today, we were talking about finding volumes of rotation. I'm making this video to make sure that you guys have the right intuition about this going into your midterm on Monday. So, let's say we have this function, f of x. Okay, let me write that a bit more neatly. This function f of x, and has this area that I'm going to shade in here, right? And we want to rotate this around the y-axis, okay? So what's that going to look like? It's going to look It's going to look something like this, okay? Right. This is sort of the shape that we end up getting, and this is a pretty, abstract shape, right? It's, maybe that's like a parabolic equation. The f of x is a parabola, and finding the volume of this is not, it's not something you're going to be able to find a formula for anywhere, right? We're going to have to figure out how to find the volume of this with calculus. So the key insight for finding volumes of rotation is that you're finding some surface area with a differential thickness, okay? With an infinitesimally small thickness. Okay? And you're integrating that infinitesimally small thickness and all the surface areas to find the final volume, right? Same thing with the washer method, right? So let's get into it. Instead of trying to solve this problem, which, trying to find the area of this really abstract shape, let's simplify the problem a little bit. How are we going to simplify it? We're going to discretize f of x, which means instead of taking graphing y for every single x value, we're just going to graph y for certain discrete x values, okay? It's the same thing you do when you're taking a Riemann sum, right? So it's going to look, so the final function is going to look, something like this. The simplified version of it's going to look sort of like this, right? Okay. Let's see, it's going to look something like, this, and then this, and then this, and then this, something like that, okay? Matches up okay. And then we're going to rotate this shape around the y-axis, okay? What I want you to notice here is that, whoops, don't want you. What I want you to notice here is that this f of x that we're dealing with, okay, if we expand it a little bit, okay, we can see that this cake shape is sort of like the discretized version of f of x, okay? Like if you take a 2D outline of this cake shape, looks like this and this and this and this. That's exactly what we were drawing here, right? Okay, that's where that came from. And when you rotate this around the x-axis, around the y-axis in this case, you get cylinders, right? When you rotate a rectangle around an axis, you get a cylinder. Let me see if I can sort of give you the intuition for that with this piece of paper. So this is our rectangle, and I'm rotating around this pivot. You can sort of tell the shape that I'm tracing out is going to be I'm tracing out a circle like this, right? But if you imagine this area carrying over all the way around, it's a cylindrical shape, right? Okay, that should be pretty straightforward to see. So now we've simplified the problem, right? We're going to find the volume of these cylinders, okay? But this is where the cake analogy, I don't really like it, because when you think of a cake, finding the volume of this cake, splitting it up into different cylinders, you're going to think, okay, this cylinder, and then this cylinder, and then this one, and then this one. It's not the right intuition, okay? Because we're dealing with cylindrical shells, okay? Not so cylinders stacked on top of each other. So this is where I think this analogy was not a great one. To stick with it a little bit longer than it deserves to be stuck with, this is the idea with the cake analogy, okay? A mathematician forces you to make a wedding cake like this using only these square cakes, okay? So what do? Well, you wrap the square cake around itself a bunch of times, and then you take a bunch of square cakes and you wrap them around themselves a bunch of times, okay? So you take one square cake and then you wrap it around it, and then so you take one square cake and you wrap it around itself, and this is like your first cylinder, okay? And then you take another one and then you wrap it around itself, and actually let's use right? And okay, so let's try to make this clear. So this is your first cylinder here, okay? This is your first square cake wrapped around itself, okay? And then this is going to be your second square cake. Oops. Your second square cake wrapped around itself. It's gonna end up being, you know, that entire thing. Okay? And then here's your next one. Okay? It goes all the way back. Okay? And it fills this entire space in. Okay? And then you have, and it feels like so the inside of it is this one big cylinder, and then there's other cylinders, you know, wrapped around it and wrapped around it and wrapped around it, okay? That's sort of how you're finding volume with the cylindrical shells. This is not, I think, a great analogy though. Let's use this image, okay? So I don't know if any of you guys remember when you were kids playing with these little cups. Basically, what you're doing with the cylindrical shell method of finding volume of integration is you're taking a bunch of these little cups, okay? And each of these little cups, right? It's a cylinder, right? Okay? It's a cylinder like this, okay? Okay? And it has a certain thickness, a very small thickness, right? They have a very small thickness. And you're saying, okay, well, the volume of plastic in these cups is what? The volume of plastic is, and let's imagine that as a kid you also cut a hole in all of these cups that you had. You're a nasty kid, you cut a hole in all these cups, okay? So what would this volume be? Well, they all have a certain thickness, let's call it dx, okay? For no particular reason. And they have, and then so to find the volume, you have to do dx times the surface area, right? The surface area of the cylinder. And as I told you, how do we find the surface area of a cylinder? So let's say I'm gonna wrap this paper up into a cylinder, okay? This is sort of the shape that we're dealing with. We can all agree this is a cylinder, no top or bottom faces. This is the cylindrical shell, okay? If I unwrap this, what we get is a rectangle, right? So we get a rectangle, and the width of the rectangle is the circumference of a circle, 2 pi r, and the height of the rectangle is going to be the height of the cylinder, right? H. So area equals 2 pi r h. And then the volume of plastic here is going to be what? Volume of plastic is going to be 2 pi r h times this little thickness, right? Okay. So you can imagine if we're dealing with some sort of super abstract function, basically what you're trying to do is it's just stacking these cups together, okay? You're stacking cups together of different heights and you can make a different shape, okay? And you're calculating the area of the surface area of these cylindrical cups times this tiny little thickness of them. You're integrating that, you're integrating over that, and then you get the full volume of any shape that you're looking at, okay? So that's sort of the image I want you to have in mind, okay? You have these cylindrical shells, okay? It's like those, you know, cups you had as a toddler. You're stacking them together and together and together, okay? And basically, you know, these heights, you know, in this case they're basically linear, but the heights could be like, you know, it could take like a curved shape, you know, it could take any other sort of function shape, and then you'd be finding the volume over that like very complicated function if you're just integrating over all of these areas, okay? Integrating over all of these cylinders, all of these cylindrical shells. All right, so let's go back to the example that we were sort of talking about in class. This is the example that we were talking about in class. We had y equals x plus 1 and y equals x minus 1 squared. Okay, so y equals x plus 1. So the first thing, again, as I mentioned, you want to draw a graph first. So we have an idea of what's going on here. Okay. Oh, well, didn't want to do that, but I guess it's been done. So what's y equals x plus 1? Well, we're going to start at 1, and we're going to draw a line, okay? And then x minus 1 squared, just a parabola centered on 1. So here it is. Here's the parabola, okay? And your first step is let's find the points of intersection here. So I kind of, spoiled it a bit. Here's one of the points of intersection. The other point of intersection is 3, okay? You guys can figure this out. I'm confident this part of the problem shouldn't be too challenging for you. Okay, and this is the area that we're looking at, right? Okay. What we're going to do now is we're going to rotate it around the y-axis, right? Rotating it around the y-axis, all we're when we rotate it around the y-axis, imagine you have to sort of have the sort of picture in your head of these shapes, just stacking up all these cylinders together, okay? All right. So for example, I'm going to draw one of them, okay? Here's one of them. Whoops. Okay, here's one of these plastic shells, and then there's going to be like another one, a bigger one, surrounding it, and so on and so forth, right? And they have this sort of tiny little thickness, okay? This is a tiny thickness. This tiny thickness, what axis is it along, okay? This tiny little thickness here, dt, let's call it tiny thickness, is along the x-axis, okay? It's along the x-axis, which is the opposite of the axis that we're integrating over, okay? So that's something to keep in mind. With the shell method, you're integrating your little dt's, you're integrating over the opposite axis of the axis you're rotating around, okay? So now we have a sort of general idea of what this is. We're taking we're taking an integral along the x goes from 0 to 3, okay? These are our x bounds. I'm just gonna say, x bounds, okay? Integral along the x bounds of all these little cylindrical shells, which we said up here, if you remember, we said you have 2 pi r h dx volume, okay? Yeah, dx there, okay? But radius changes and height changes. Doesn't it? Radius and height of these cylindrical shells changes as a function of x. So the challenge with these sort of shell method problems is you want to find expressions for r of x. You want to find expressions for r of x and h of x. This is really like the sort of, this is the sort of tough part, so to speak, okay? It's not tough for you guys. You guys are going to do great. Okay, so here's what we need to do. Well, okay, radius is typically going to be very simple to find, okay? Radius, you don't need to worry about it. Radius, in this case, okay, so what are the radii of the cylinders, okay? There's one, there's another, and they keep going out and out and out. the radius of each of these cylindrical shells as you integrate over x is just going to be x, okay? The radius of this cylindrical shell here, when you're at point x, is just x, right? Okay? Makes sense. Simple enough. Whoops. Okay. So integral 2 pi x. I mean, you can just take the 2 pi out of there. And then h of x. H of x is not the issue, okay? So h of x in this case, what is the height of x, okay? So basically, you have these. Basically, now it's more instructive to sort of have a 2D view of things, okay? Okay, so let's do that. All right, basically, what we're doing here is we're taking these vertical rectangles, right, along this shape that looks like, Spider-Man's lenses. Okay, these, have infinitesimally small thickness. Okay, so we can just say that it's 1 point x, x1, x2, blah blah blah. So at this x1, what's the height of this cylinder, right? The height of the cylinder. What's the height of the cylinder of this rectangle at that x? So we know that, just zooming out, this is dx, and then what's the height? Well, the height is just, x plus 1 here minus x minus 1, okay? It's x plus 1 and then x minus 1 squared, right? The height is just x plus 1 minus x minus 1 squared, okay. Simple enough, right? That's it. You just have to figure out, you just have to sort of orient yourself, okay? You have to have the image in mind, you have to draw your rectangles, and then once you have your rectangles, and you figured out the height of these rectangles, you figured out the height of your cylinders, and you just integrate over x. Our x bounds are from 0 to 3, okay? Integrate over x.